Laws of exponents. Today I would like to talk about the few laws of exponents that we have already covered in previous lessons, well, maybe last year or somewhere around then. These laws are essential for what follows in mathematics, so let me give you some brief reasons for each of them. So let me start first by the definition of the power. So imagine you have a power a to the power of n. Okay, so the meaning of such a thing, as explained in the previous lesson, the last lesson, is as follows. You have to multiply a times a times a and do it n times altogether, and what you get is a to the power of n. A here is called the base and n is called the exponent, or sometimes we call it an index or a power. Okay, so this is the meaning, and this understanding of the power is essential for what follows. Okay, so I will write this in exponent. Okay, now let me start with these laws. So the first law is here: to multiply numbers with the same base, keep the base and add the exponents. So here is the law: a to the power of m times a to the power of n equals a to the power of m plus n. Now, to show you why this makes sense, let us do it with a simple example. So imagine you have a to the power of 3 times a to the power of 2. Okay? Now let me translate these using the definition of the exponent of the power, what the power means. So this has to be, as a to the power of 3 is a times a times a, this should be multiplied by a to the power of 2, which according to the definition is a times a. So you see, altogether we have a multiplied by itself 5 times. 3 times here, this is 3 times, and 2 times here. Okay, so altogether it's multiplied 3 plus 2 times. So according to the definition, this should be a to the power of 3 plus 2, or a to the power of 5. Okay, so a to the power of 5. Now you can imagine why, when in general case we have a to the power of n, a to the power of n times a to the power of m, that this should have the answer a to the power of m plus n, because the first product contains n factors, so this contains n factors of a, the second one contains m factors of a, and altogether there are n plus m factors of a. So it's a multiplied by itself n plus m times, so it must be a to the power of m plus n. So this is the reason behind this law. It's very simple. We shall use it in what follows. Now, the second law. The second law has to do with the division. So, to divide numbers with the same base, keep the base and subtract the exponents. So, okay, so the law says a to the power of n divided by a to the power of n equals a to the power of m minus n. There is a condition that has to be satisfied. For this to make any sense, a cannot be 0, because if a was 0, there would be 0 here in the denominator for positive n, and therefore you would run into trouble. So therefore there is this essential condition that has to be true: a is different from 0, so you have to have a non-zero base here. Now, to give you an example why this works, let me start with particular numbers. So a to the power of 5 divided by a to the power of 3, say. Okay, imagine you have something like that. Now, if you use the definition of the base, of the power function, or of the power, what the power is, what you get is that in the numerator you have a multiplied by itself 5 times. So it's a times a times a times a times a, okay, like this, 5 times. And in the denominator you have a multiplied by itself 3 times. So it's a times a times a. Now you can see that some of these factors can be cancelled. So you can cancel this a, this one and this one, and these two. So what remains are 2 factors of a in the numerator, and altogether it's then a times a, which is a to the power of 2. But this number 2 here can be understood easily. It's 5 factors of a minus 3 factors of a. So it's 5 minus 3. So this number here is 5 minus 3. Okay? So this is exactly the law that we are showing or trying to prove, that a to the power of n divided by a to the power of n is a to the power of m minus n. So there, in general, if you had a to the power of m divided by a to the power of n, there would be m factors of a in the numerator and n factors of a in the denominator of the fraction. And if you cancelled some of them, well, actually all of them which are in the denominator, you would end up with a to the power of m minus n, like you saw here in this particular example. Well, there is more to this law than seems at the first sight. Well, it may be interesting when m is less than n. To give you an example what happens here, imagine the situation like this. A to the power of 3 divided by a to the power of 5. Okay? According to our law, this should be a to the power of 3 minus 5, which is a to the power of negative 2. Okay? So we have to assign meaning to expression like this. So what is base multiplied to a negative power? To see what it means here, let us look at this fraction and try to replace a to the power of 3 according to its definition by a product of a times a times a divided by and a to the power of 5 by a times a times a times a times a. Okay, there are 5 factors of a, and then we can cancel these, and what remains is 1 over a to the power of 2, like you see here. So it has to be the same thing as the one here. If this law is to be true, these two things, these two expressions have to be the same. So in case that m is less than n, you get the power with negative exponent, and the meaning of this power with negative exponent is that it's a fraction 1 over something. So for example, if I have to generalize a situation, imagine that m is less than n, and then a to the power of m divided by a to the power of n is a to the power of m minus n, which is the same as 1 over a to the power of n minus m. This time n is a greater integer minus smaller integer, so you get positive integer here in the exponent in the denominator. So in our case, if m is 3 and n is 5, so what you get here is 5 minus 3, which is 2. So this is the, well, some interesting note regarding this formula, and I'll come to this a little bit later, what the meaning of the negative power is, but now let me continue with the next law. So the next law says, when raising a power to a power, keep the base and multiply the exponents. So you have a formula, a to the power of m, all that to the power of n is a to the power of m times n. To give you a particular example, imagine you have to evaluate a to the power of 2 all raised to the power of 3. Okay? Imagine that. So now if we want to evaluate this, or actually try to simplify this or convert this to a different form, we can use the definition to replace a to the power of 2 by a times a, okay, like this. And this is raised to the power of 3. So what do we do when we raise something to the power of 3? We have to multiply it by itself 3 times. So we have to multiply a times a, then times a times a, and that times a times a. Okay, so the base now is a squared, a times a, and this is multiplied by itself 3 times. And now you can see that you can remove the brackets without any trouble there. They are not essential here. So if you remove the brackets, you have a product of exactly 6 factors. So there are altogether 6 factors. 6 is like 2 times 3. So there are 3 pairs of factors. Okay, 3 pairs of factors of a. 3 times 2 or 2 times 3, whatever. So it's a to the power of 6. Okay, so it must be, as you can see, a to the power of 6, where this number 6 is obtained as a product of these two powers. So in general, if you have an expression a to the power of m all raised to the power of n, what do you have here? You would have the base, which would contain a times whatever, how many times? Well, you can say it's m times here. It would be m factors of a, and all that would be multiplied by itself, and it would be multiplied n times, and therefore altogether you would have m times n factors of a. So it must be then a to the power of m plus m times n. Okay, so this law works very nicely. It's very interesting and simple to understand, actually. Okay, now another law. The power of a product is the product of the powers. So these laws, these two laws that follow, are of a somewhat different kind than the previous ones. Okay, so let me look at them here. So you have a times b to the power of n. Let me use a particular example, a times b to the power of 3. Okay, to do it you have to use the definition. So the base here is a times b, so you have to multiply the base by itself 3 times. So it's a times b times a times b times a times b. Okay, I'm not writing down the multiplication symbol here. So you can remove the brackets and see that you can group a factors together, and you see that it's a to the power of 3 because there are 3 factors of a, and you can group b factors and you get b to the power of 3. So it works very simply. When you have a product raised to the power of n, you end up with n factors of a using the definition and n factors of b, and therefore it has to be a to the power of n times a to the power of times b to the power of n. So this should be also easy to understand. On this particular example, it works the same for a general case of general value of n. Now let's look at the following one. The power of a quotient, po slovensky podiel, the power of a quotient is the quotient of the powers. So you have a over b as a base, and this is raised to the power of n. Again, let us look at a particular example. Well, there is one thing here. This condition has to be satisfied. B has to be different from 0, and the reason for that is obvious. If b was 0, you would have to divide by 0, and it would make this situation complicated because the expression would have no meaning. So imagine a particular example of n equal to 3. So imagine you have a over b all raised to the power of 3. According to the definition, when you take as a base the fraction a over b, this should be a over b times a over b times a over b. Okay, like this. And if you have this product, there are this is multiplied by itself 3 times, you can use the rules of algebra to simplify, and you can multiply the fractions, multiplying their numerators, and get the new numerator. So on the top you have a times a times a, which is a to the power of 3, and in the denominator you get b times b times b, which is b to the power of 3. And you see it really works for this particular example of n equals 3. It would work the same for any value of n you can imagine, any integer value of n you can imagine. Okay, so this is the power of a quotient, is the quotient of the powers. This is this law of exponents. Now the last two laws, and these are quite interesting and quite different. So many times you will run to this expression a to the power of 0. So here this condition has to be true, that a is different from 0. So we are talking about a situation when a is different from 0, and we want to assign some meaning to a to the power of 0. So what is a to the power of 0? Now, to understand this, you can use two ways, but I will show you the first one. You can imagine that 0 here can be expressed as 1 minus 1. So you can write this 0 in a convenient way as 1 minus 1. And now you can use the law, which is here, this law, a to the power of m minus n equals a to the power of m divided by a to the power of n. If you use this law here, this means that this should be a to the power of 1 divided by a to the power of 1. Okay, so whatever a to the power of 1 is, it is the same here as here. So therefore these two numbers are the same, and you can cancel them out. And what you end up with is just number 1. Okay, this cancel with this, and you get 1 as an answer. The same answer would be obtained if you replaced 0 by 2 minus 2. You would have had a to the power of 2 divided by a to the power of 2, and so on and so on. So this really is not dependent on the way how you choose this convenient 0 here. It's always 1. You can also see why this condition a is different from 0 has to be satisfied for such reasoning, because you see there is always this a to the power of 0 is replaced by a fraction, and the fraction has a denominator which cannot be 0. And if a was 0, a to the power of 1 would be 0, and you would have to divide by 0, which you cannot. So this is the reasoning behind this law. Now there is the last one, the power with negative exponent, powers with negative exponents. This is called like this, but it's just my name for this law. It's not official name. Okay, so we have this law written in two formulae like this, and one particular case of this formula. So imagine you have a to the power of negative n, and you have to understand what it means actually. So again, try to express negative n as a to the power of 0 minus n, okay? This can be replaced because you see minus n is the same as 0 minus n. Now use the same law as before, and this should be a to the power of 0 divided by a to the power of n, okay? And this number here in the numerator, as you know from these previous considerations here, is just 1. So it's 1 over a to the power of n. And you see this is this first formula here. Of course, a cannot be 0. This is the same condition that has to be satisfied as before for the same reason. But you see how it works and how you get this answer. Now, if you want to see why this second answer is true, you can use many ways to prove it, but the one that I choose here is as follows. Imagine I have this, well, I will write it here. I have this equation which was proved here, and write it again. A to the power of negative n equals 1 over a to the power of n. Now, I will try to express this. How do I do it? First, I multiply by a to the power of n. What I get is a to the power of negative n times a to the power of n equals 1. And now when I want to express this, I just divide by a to the power of minus n, and what I get is a to the power of n equals 1 over a to the power of negative n. This is actually what we wanted to show, and this is this formula here. Okay, so this makes or completes this proof. Now there is one special case of this first formula, a to the power of negative n equals 1 over a to the power of n, and that's the case of n equals 1. So if you take n equal 1, you see that a to minus 1 equals 1 over a to the power of 1, which is 1 over a. Because we know that a to the power of 1 is just a multiplied by itself, well, actually, there is just one factor of a. You just end up with this, because a to the power of 1 is a.